Let us practice the line integral using the following exercise. We want to compute the line integral of the vector field f arrow dr, where the curve C is a straight segment AB, and A and B are 2 points in a three-dimensional space with coordinates 1, 2, 3, and 5, 1, 7. And the integrated function, the vector field, at the point x, y, z, has the following 3 components of the result: y, z, and x. These may be any 3 functions of x and y and z. So first we want to write some parameterization of the segment AB. There are infinitely many parameterizations of this curve, but we can write that the general point x with coordinates x, y, z will be A, 1 point, plus the parameter t times the difference b minus a. And t then runs from the interval from 0 to 1. If t is 0, then we are at A, the initial point of the curve. And when t is 1, then A plus b minus a is b, the endpoint. This is perhaps the first, the simplest, straightforward parameterization of such a segment. So, this is in the vector form, and let's write it in components. X starts at 1, and when t reaches 1, x should reach 5, so we must add 4t, the difference of 5 and 1. Similarly, y starts at 2, the y coordinate of the point A, and when t reaches 1, y should decrease from 2 to 1, so the difference is minus 1, so y is 2 minus t. And finally, z starts at 3, and it should go up to 7, so we must add 4t. Then we can prepare either the derivative or the differential. dx is 4 dt, dy is minus dt, and dz is 4 dt. Well, and then we can write the integral if we denote it capital I. So if we rewrite f dr as f1 dx plus f2 dy plus f3 dz over the curve C, then we can rewrite this as the definite integral with the integration variable t. So t goes from 0 to 1. Now f1 is equal to x, and x is equal to 1 plus 4t. And we multiply by 4 dt, we write 4, and we factor out dt and we write it at the very end. Plus f2, which is z. Z is 3 plus 4t, times dy, which is minus dt, and we write dt at the very end. Plus f3, which is x. X is 1 plus 4t, times dz, which is 4 dt. and this is integral from 0 to 1, and we can simplify this a little. We have 4 plus 4 is 8, minus 3 is 5. Let me check. No. Sorry. The first component is y. Sorry. The first component of f is y. So instead of 1 plus 4t, there should be 2 minus t. f1 is namely equal to y, and y is 2 minus t. So we have, 8 plus 4 is 12, minus 3 is 9. And now we have 16t minus 40 is 8t. dt. The antiderivative is 9t plus 4t squared from 0 to 1, which is 9 plus 4, which is 13. So this is the value of this line integral of the vector field f along the segment, along the curve C.